Hi all, welcome to this new video. So for the moment, we have covered all the notebooks within these advective barriers folders. So we've essentially been looking for advective barriers in two-dimensional velocity fields. Now we will instead be focusing on so-called diffusion barriers. As you will see, most of the techniques that we used to extract advective barriers also apply to the diffusion barriers with some mild modifications. The first thing, the first diagnostic we'll be treating is the so-called DBS, which stands for Diffusion Barrier Sensitivity. And it is, as you will see, fairly related to the FTLE field, both in terms of computation, but also in terms of the visualization of the results. Of course, the main notebook is inside this main folder, and we've been extracting this diffusion barrier. So we've been computing the diffusion barrier sensitivity on the Agulhas region. So actually, yeah, if I click on the notebook, so again, we will need to import the statements as usual. So this is pretty standard, as we've done also in the advective barrier case. Now, as a little background to diffusion barriers and what distinguishes diffusion barriers to advective barriers, or to so-called LCSs, Lagrange covariance structures. Well, first of all, a material surface is denoted as a diffusion barrier if it is a structurally stable extremisor of diffuses transport relative to all neighboring surfaces, whereby the structural stability implies that the barrier, so the diffusion barrier, smoothly persists under tiny perturbations in the underlying velocity field. So the question is now, what is the difference between LCSs and diffusion barriers? So LCSs were essentially material structures which are the most influential, and by influential I mean they are either the most stretching or the most shearing surfaces that block advective transport. Now, this influential surface is not a trivial statement, because actually all material surfaces, by definition, block advective transport. So if you pick any material surface, then of course particles will not move through the surface, and hence any material surface is actually blocks the advective transport. So what we were looking for in the LCS case is we were looking for the most influential ones. So the question you were asking is, okay, which is the surface, or which is the line for the 2D case, which is the material line which is stretched the most, or which is the material line which has the highest shearing. So that's the type of questions that we were looking for in the LCS case. Now, in the setting of diffusive transport barriers, you do allow some degree of diffusion throughout these barriers, but you're interested in finding the most the extremizing the material surfaces which minimize or maximize the diffusive transport across it. And we'll be primarily focused on weakly diffusive transport, so kappa, which basically measures the amount of diffusion. Is fairly small, as this is essentially the physical most relevant range for processes in nature. Actually, the first 4 steps, so in terms of structure of the notebook, the first 4 steps are essentially the same as also in the advective barrier case. So importing dataset, defining the main parameters, and then interpolating the velocity field from the discrete grid data. Then we compute the so-called diffusion barrier sensitivity. So the first thing that we need to do is we need to compute the gradient of the flow map over the mesh grid using an auxiliary grid. So this is essentially the same as we've done also in the FTLE computation. Then we need to compute the so-called time average diffusion Cauchy-Green strain tensor. Now, what is this time average diffusion Cauchy-Green strain tensor? You basically, so it's denoted as CD, and it's an averaged Cauchy-Green strain tensor. So basically, if we consider the FTLE case, in the FTLE case, we were just basically interested in the Cauchy-Green strain tensor from time T0 to Tn. Here, you take the averaged Cauchy-Green strain tensor over the time interval. And it's not the usual Cauchy-Green strain tensor, but it's a Cauchy-Green strain tensor, which also has diffusion component. So actually, if you write this out, then you can see that this diffusive or diffusion Cauchy-Green strain tensor CD is actually the determinant of the diffusivity tensor, which can generally be varying both in space and time, and a so-called transport tensor, where the transport tensor has simply this form. It's the gradient of the flow map, actually the inverse of the gradient of flow map, then the diffusivity tensor, and then again the gradient of the flow map, and you simply take the transpose then in the end, so the negative transpose actually here. And you call T simply as the transport tensor. Now, this diffusivity tensor denotes a continuously differentiable positive definite diffusion structure tensor with possible anisotropy and temporal variations. What we choose in the script is the so-called isotropic diffusion. So this tensor D is simply chosen to be unity. And in that case, the transport tensor simplifies to this. Then you compute the diffusion barrier sensitivity. So again, we basically have to, at every point, we have a so-called time average diffusion Cauchy-Green strain tensor. And then from this time average diffusion Cauchy-Green strain tensor, you simply compute the diffusion barrier sensitivity by taking the trace of this tensor. And then you plot the diffusion barrier sensitivity over a field of initial conditions, basically. You can see that there are a lot of steps here which are similar to the FDLE computation. The first one being that you require the gradient of the flow map. And however, there are some mild adaptations. It's a bit more involved mathematically. So I invite you to check out actually the paper or their notebook section in the references. And actually ridges. So if you compute it in forward time, then ridges of this DBS field will coincide to barriers which maximally inhibit the diffusive transport across it. Whereas if you compute it in backward time, then ridges of this DBS field will represent essentially structures which enhance or maximize the diffusive transport across it. So I won't go through all these steps now again, because it's essentially the same as in the previous script. It's just like copy pasting. So actually these four cells are just like copy pasting the part from the advective barrier case. Now, in terms of the DBS, again, I import all these parallel functions because the computations have been largely parallelized. So that's why basically I take all initial conditions, vectorize them, and put them into different batches. And once I've done that, I compute basically this DBS for each initial condition. So I compute the diffusion barrier sensitivity for each initial condition. In order to do that, I simply first need to actually compute the gradient of the flow map. This part so I need to first compute the trajectories. Why do I need to compute the trajectories? Because I then need to evaluate the diffusivity tensor along the trajectories. Okay. Now, in our case, one could actually get rid of it because the diffusivity tensor is anyway constant both in space and time, but generally the diffusivity tensor might be varying both in space and time. So you would need to compute this diffusivity tensor along the particle trajectories. That's why I need the particle trajectories here. Then, of course, I need the gradient of the flow map. And from the gradient of the flow map, I then simply compute here in this first step, I simply compute the averaged Cauchy-Green strain tensor. This is done in this diffusion Cauchy-Green function, which you can find in the subfunctions folder, which takes as input simply the interpolant for the individual components of the diffusivity tensor, the trajectory, the time, the gradient of the flow map, and then simply the length of trajectory, and then the length of trajectory, and then finally you can actually also specify. So this is basically some averaging parameter. Essentially, when you do the averaging of the Cauchy-Green strain tensor, you don't want to actually. One thing, of course, you can do the averaging over all times, However, this is computationally quite costly. So what one does is one doesn't do it over all times, but just over a subset of times. So basically, you leave out every n time steps and just do the averaging over this smaller set. But actually, this is just in terms of computational, to save computational time, and will not drastically influence the results. Hence this number of averaging parameter. And once you've done that, you simply pass this average Cauchy-Green strain tensor into the DBS function. So this function here, you can actually find it here. So it's inside this notebook. What it does, it simply takes as input the average Cauchy-Green strain tensor, so the average diffusion Cauchy-Green strain tensor actually, and simply computes the trace. So this is simply computing a trace. And then as an output, you get the diffusion barrier sensitivity for each initial condition. Now, of course, what you get here, this needs to be vector. Sorry, this needs to be reshaped to a mesh grid so that you can plot it. And actually, what I've done here is I've simply defined the diffusivity tensor. So here it's the definition of the diffusivity tensor, and it's assumed to be constant in space and time. Now, of course, you can make it to be temporally varying and also spatially varying. That's also okay. You would just need to basically define it here appropriately, and then the function will take care of it. So we just need to redefine this diffusivity tensor appropriately here. Here is what I said previously. So the number, you can specify the number of diffusive Cauchy-Green strain tensor used for averaging. So when we need to average the diffusive Cauchy-Green strain tensor, then you can specify the number in. If you want all, then you can simply set this parameter to 1. So basically, if you want to compute this integral and then averaged over time as accurate as possible, you simply need to set this parameter here to 1. As you will see, the results will not drastically change between 1 and 10. So that's why I chose 10, simply to save computational time. That's pretty much it. So we can now plot the results. And as you can see, so we plot this of initial conditions, and you can actually then compare this DBS field to the FTD field. They will share a lot of similar features. Now, they don't exactly coincide, but the features will be fairly similar, I would say. And these ridges here, for example, so these ridges here indicate the most prevailing diffusion barriers. So these ridges here, if you compute them, so in forward time, these ridges will inhibit the diffusive transport across it, whereas if you compute it in backward time, then ridges of the DBS field will show diffusion enhancers. With that, I want to thank you for your attention, and in case you have any questions, then just feel free to drop me a mail.